Oh, there's Ethan. No, I will probably, well, I'm going to take a look at the schedule today. I might have a new lab to turn in tomorrow. I mean, handout to turn in. Oh, goodness. Yes, it's Monday. I'll have a new lab to hand out tomorrow where we kind of take a look at some resonance. I mean, observing the effect like we do in the chapter and whatnot. As far as doing a lab for resonance, it's a little more boring than it sounds, I guess. Now I'll take a look and see if we have something interesting. But I do have in mind a couple of labs that we will be going through to finish off our time here. So we have this week, and then next week we're off for the holiday, and then I think we have basically 2 weeks after that. Well, that's including the final with that as well. So, excuse me. Well, let's see what we got here. 2, 4, 6, most of the class. So, so without further ado, further or lesser, we'll take a look. Oh, that is not the screen I wanted. Hold on 1 second. Try that again. Coming up. No, it's not. All right. Oh, my mouse is being finicky today. All right. Well, oh, yeah, if you remember last we left off, we are talking about the Q factor, about more balanced circuits and such. Um, just to give you a brief, I won't go over Q factor again, but so today we begin with the last half of the chapter talk here, where the bandwidth of resonance circuits. So we're gonna, so it's an interesting term, actually, bandwidth. I know everybody, especially these days with the wide usage of internet and everything else throughout it, everybody runs into this word. But you would be amazed at how many people do not know what this word actually means. So we're going to kind of take a look at that today, and you're going to be one up over the crowd, I guess. So now this pertains, of course, we're still examining LC circuits, or you could even say RLC circuits, if you will. Um, and if you recall from before, from the formula that we used to establish resonance, right? Let's go and let me take a little peek for you, just to bring it up. Yep, that formula right there. So here's what we're doing, right? We're going to set X of L. So if we wanted to make a resonance circuit, and we know that we're going to use these components, the first thing we would do is we would set the inductive reactance to be equal to the capacitive reactance. And once we do so, then we establish grounds for this formula here for frequency, right? F sub R, resonant frequency, is equal to 1 over 2 pi square root of the inductor value times the capacitive value. And this basically deads by the value of the components, it locks us on to a particular frequency. Now, sorry, scrolling through there. So when we do that, we do establish one particular frequency. Now, if you recall from the graphs, and this can be due to our Q factor, right? So we could have a certain amount of components would work well and some is more well than others, right? We have a much higher Q factor, in which case we have a much more stable circuit, sharper, if you will. Um, and that's where this starts to come into play, where we look at, okay, this is true for maximum resonance effect, meaning, okay, so at this particular peak or this particular frequency, here's our established resonant frequency. But based on the graph, see, if we take a look at the next slide here, if we look at this graph here, see, and you'll see that on the bottom, what are we measuring here? So we're looking at the current versus the frequency, okay? Now notice right in the middle, okay, that's our F sub R. That's our peak. This is the most, for this particular circuit with the values that are chosen, okay, at 50 kilohertz right here is our dead center frequency that we like. However, you'll notice that the 70.7 response line right here that we established that our bandwidth overall is 20 kilohertz. Now, what the heck does that mean? Well, our center frequency is such, but the circuit will still work with frequencies as far out as this. So overall, if we look, our circuit is capable of running frequencies anywhere from 40 to 60 kilohertz, ideally being the 50 kilohertz line, but it's acceptable to run all the way up or all the way down to from 40 to 60 here. And that is what we mean by the bandwidth. It's like, how much room do we have to play with? Now, anything past that, you'll start to experience, it can depend, but more often than not, what we would experience is distortion. The frequencies would have a difficult time getting through the circuit. The components wouldn't be working optimally with it. So their charge discharge effects would not be going with this frequency really well. Excuse me. So as long as we operate within our bandwidth, though, our circuit is going to work beautifully. I mean, ideally, of course, right, being the 50 kilohertz, but if we were to run like say 45 kilohertz, the circuit would still perform well. We wouldn't notice any distortion, any attenuation. And attenuation, that's the effect where you start to get dampening on the signal, so the overall magnitude wouldn't be as high as it could be. It's like if we were running 5 volts on the output, attenuation would start bringing it down, and over time it would bring it down to 0. But you'll start seeing it fall off. It wouldn't be hitting the 5 volts. It would be stepping down, boom, 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 little by little. So you can't experience attenuation. Distortion being where the signal's not optimal, where you're getting some kind of frequency out, but it's all kind of wavery, so you wouldn't have like a steady state signal. And these are not optimal effects, basically, okay? So this is what we mean when we talk about the bandwidth of the tuned circuit. The circuit works ideally for this, and anything else, not so much. So you can see if we ran the signals through from 0 to 100 kilohertz, what we see from like 0 to 20 or 80 to 100, not so great. But like I say, from the 40 to 60, that's our acceptable bandwidth for this particular circuit. This thing will perform well. So then we get into something where we call it tuning. So what we try to do, we'll get the resonance of different frequencies, okay? So we change the value. We will either change the value of the inductor or we'll change the value of the capacitor. Very typically, I'll be honest with you, and with the components and whatnot, it is much, much easier and more stable to change the value of the capacitor than it is for the inductor, just for the type of feedback that you get and such. And let's see here. So as he states in our illustration here, Yeah, see, the variable C can be adjusted to tune this LC circuit to resonance at any one of these 5 different frequencies. So if we went through, let's take a peek here, right? So we got our coil. There's the internal resistance factor there, and down here we've got a tunable capacitor, if you will. So as we tune the capacitor, we get different center frequencies based on the value of that capacitor. So ideally, we could set this thing for these specific frequencies right here, and we would have a new center frequency for each one. See that? So this thing is very capable of going through and tuning to these different frequencies, a lot like radio, even television, if you will. They all run on different frequencies. And so when you tune to that specific channel, okay, you're getting that center frequency. And that's why you notice sometimes if you tune, I don't know, let's say you listen to 105.2, okay? So if 105.2 is your station, uh, and now we could still possibly hear the signal at a little different frequency than a 105.2, if 105.1, but you start getting, noise. It doesn't sound real clear. And the same with 105.3. You possibly might still get the signal, but a lot of noise. It's not getting the where it wants to be as far as the bandwidth is concerned. So this is what this is setting it up for, right? Communications, getting different center frequencies, and how we obtain them. And you can see it's as far as filtering through and getting a lock onto these different frequencies is just as simple as tuning that capacitor. Our energy source would be capable of delivering all of these different frequencies. You just have to tune it to the particular one you want. And that's where we're going with this. Now, let's look a little further here, if you will. So then we go and draw out a graph, if you will, where we show our frequency range. All right. You can see he even stated where frequency low and a frequency high, and gives a particular capacitive value for that, or our ideal like middle ground here, if you will. If we tune the capacitor into the middle, our middle frequency here is the 1080 kilohertz. So this is very, very typical of how you would tune, a receiver to hit the pop or carrier frequency that we would like. That's why if you ever manually tune your radio, you'll go through these different frequency ranges. And a lot of times, what do you hear? You hear distortion, noise. There's nothing, there's nobody broadcasting on that particular frequency. And then all of a sudden you lock on, boom, now you get crystal clear signal. Well, that is being broadcast on that frequency. And they go through and they try to, like the FCC regulates this and whatnot, and they try to go through, where we end up getting crossover in different regions and whatnot, and they try to balance it out so that way no two radios are sharing the exact same frequency in proximity. So maybe like in Southern Illinois, they might be using such and such a radio station, and you wouldn't want to be using that same exact one in like Central Illinois, because the possibility of crossover where the two radio stations would be fighting that frequency, they exist. So then they alter it from region to region, and you get different ones, of course. But this is a very simplistic little guy here. You see where RF signals coming through a coil, okay, and transferred over to our other coil, if you will. And yeah, air is our medium. There's not an actual like hard wire in this case, okay, coil to coil transmission. and that's our range, and that's how you would set it up and show this is our capacity. Our overall bandwidth is such based on the tunable or tunability of the capacitor. Uh, but that's really all it comes down to when you say tuning, is you lock on to a specific frequency. And so based on your components, you can make a table like this, right? So if we had a 40 to 360 picofarad capacitor and our coil is locked in at the 239, we would use that formula and find out what our overall range is, okay? So at the very bottom, I just plug in the 40 into that formula, you know, the 1 over 2 pi square root of L times C. That would be the one I would use. And so I would use the lowest one, establish our low end, and then, of course, use the highest value to establish the high end, and then cut it in the middle, and that's our middle frequency, and all frequencies in between are what we could use. And it's something very similar. I mean, that's how they set up for, and we'll have like a certain range for like AM radio, right? So AM's got a certain frequency range, and that would be like something like this. And then FM, and we could go into ham radio, you know, the military, police bands, and oh my God, there's so many radio bands, right? Marine bands and whatnot. We could do this. We could do this for quite a while, actually. All right. So then he goes in to talk about, well, of course, if we're going to talk about tuning, we have to talk about mistuning as well. So what the heck does that mean? So we bring back our Q factor, and we're going to examine that with the mistuning. Now remember that our Q factor can be quite different depending on the components that we have chosen. And in some ways, that's why radio does tend to be more expensive, because they are locked into specific components. And a lot of times, especially for radio, they use high-end componentry and whatnot. So that does get quite pricey. But in any case, so mistuning. So when you have a frequency, okay, and of course we have an input voltage, there's always going to be some sort of magnitude that we're dealing with, even if it's very, very minimal. In a lot of cases in radio broadcasting, you try to keep your power as minimal for broadcasting purposes, because the signal will degrade over distance and whatnot. But anyway, so when the frequency of the input voltage and the resonant frequency of the series circuit are not the same, okay, this means you're trying to put something into the circuit that it doesn't quite like. The mistuned circuit will have very little output. And that would mean, you know, we're working outside of the range of what these components are established for. So now if this frequency comes through, what happens to it? All right. So as you can see, he says that the mistuned circuit has very little output compared with the Q rise in voltage. So we're still going to get a response. I mean, we have an energy going through these components, and they're going to react, okay? But how they react, that's the key. That's the interest here. So now, if we've gone through some of these circuits, we'll notice, see, like when he makes a statement with the parallel circuit, that when it's in this tune, it does not have a very high value of impedance, whereas a series one would. And it's just the nature of how that's laid out. Now, if you remember looking through how we what goes on with the capacitor values, especially when we're in a parallel mode, and how that happens, and that would be why we would have an extremely low value of impedance based on our capacitive value, right? The 1 over 2 pi FC, and it's so that's a direct relationship with that. So any case, so when you get this net reactance where it's off, yeah, off resonance, out of resonance, it makes this LC circuit either swing one of the two ways. It's either going to become a much more inductive or much more capacitive. In either case, it would be imbalanced, where now our X of L no longer equals our X of C on any plane, and it throws the circuit way out of whack. And again, so it would swing it either very inductive or very capacitive, partly, depending on A, the configuration, and B, the value of the components that we're dealing with. So kind of the key here, okay, because he keeps talking, he's going to keep talking about parallel circuits. Well, ideally, that's what we're looking at. And why is that? Well, see, if we look at the circuit here, he's using the reciprocal method to establish what our overall or equivalent impedance is for this circuit. So, and when that, right? So how do we do the reciprocal method? Everybody should recall that it's the Z1 times Z2 times Z3, et cetera, et cetera, et cetera, over the Z1 plus Z2. So if we end up changing these values because of the parallel mode and because of the reciprocal style of getting the overall impedance, that's the key here. So parallel resonance is much more complex than series resonance. And it is actually, because the reactive branch currents are not exactly equal when X of L equals X of C. So even though we've set these factors to equal one another, they're not going to, like, as far as the current split, because current is going to split, right? We have a parallel network. So we have a total current going in here, and then it's going to split between the two legs. It's not going to be equal, even though we've stated that, okay, these two components should, as far as reactance concerned, still equal out. Well, this is the real world now, right? In the real world, it's still a capacitor and it's still an inductor. And even though we've gone through the trouble, with this established frequency that these two reactances should equal out, they're still going to be true to their nature. And with that, we're going to have some slight, and it's not a lot, but it is there. There is a difference. The coil, as you see here, the coil has a series resistance RS and that branch. So we do have a bit of a DC resistance going on. And compared to the capacitor, which only has itself or its own reactance to deal with. So because of that internal resistance of the wire and the inductor, it throws it off. All right. If the copper wire were resistance free, okay, like in the ideal world, which doesn't exist, right? Then we would have this. But because the coil has its own bit of internal resistance, you're always going to have a variance in this style configuration between these two components. And it's something to note. Now, notice though, from a point I was making previously about that Q factor, if, like he says here, for high Q circuits, we consider RS negligible. And why would that be? Well, for a high Q circuit, you've seen if you guys remember from a previous example, how we looked at that roll off or display where it showed the magnitudes and whatnot of the ground. Here, let me go back. I like pictures to go with it. Yeah, so if we look at our Q factor, even though both of these still have the same LC ratio, because of the components involved, one, let's see, like this circuit on the right here has a much tighter bandwidth than the one on the left here, the red one. And notice the Q factor involved. So this guy on this side would be the type of circuit he's referring to, having a high Q factor. It's much more in balance with itself, or as far as like our X of L equaling our X of C, these guys would be much tighter ratio than these guys would be. Yeah, there we go. Anyway, where were we at here? We were here. And that's what he's saying by that statement. So when you go through the homework and you go through the book, remember what we're going with here. So he'll continue on and with our analysis of parallel resonance circuits. So now in a low Q circuit where we just happen to pick arbitrary elements for our components, not a great Q factor with them. So with that in mind, there are a few things we'll have to take into effect here, right? So overall, we'll examine the circuit, come up with a Z equivalent, we establish what we are. Okay, in this case, our impedance in this leg is here, and our impedance in this leg is here, like such. And then, oh, but yeah, that's really what he's talking about with that, examining this and trying to set up. You could see even from the formulas that we are always going to be slightly off. And so if we raise our Q factor up, we minimize the effect of the R sub S here, the resistance of the coil. So something to keep in mind. So now, yeah, here we go. I hope everybody loves parallel circuits because that's what we're gonna do. All right. So we take a look at it. I'm going to start with figure A right here. Okay, we got a very typical RLC circuit. Okay. And we still have a Q factor here, a nice high strong one, Q of 100. So how do we attain it? Resistance over to X of L gives us our Q factor. So the shunt, okay, the R of the parallel across the inductor and the capacitor is a damping resistance because it lowers the Q of the tuned circuit. So RP may represent the resistance of the external source, okay, or it can be an actual resistor placed into there to try to, induce this effect, if you will. So using the parallel RP to reduce Q is better than increasing R sub S. So what he's saying is, like, if we were to try like a different inductor to try to obtain a good internal resistance value, that it's much easier to use an actual resistor in tune with that. So, because look what he's chosen. Like if we looked at figure B here, all right, we got an internal resistance of 5 ohms with the X of L reactance of 500 and the X of C reactance of 500. But look at like circuit A here. He's putting in an actual 50K. Now remember our ratio. So 50K and compared to a 5 ohm. 5 ohm is virtually negligible at this point, right? And that's what we're examining. So really, when you come down to it, I mean, in a realistic world, ideally this bottom circuit C here would be really what you're dealing with, okay? And look at our difference. So we've gone from this to this, and now our best circuit would be this one here. We've gone through and put a 50K in parallel with these two other guys to help balance the circuit, or damping, if you will. And you'll notice this a lot of times. Well, because again, it's one thing from dealing with the ideal world where it looks great on paper, but in reality, when you go and put it into effect, if you just have the inductor and you just have the capacitor and no damping resistor involved in this case, it tends to have the circuit tends to be more erratic, if you will. It's more capable of flyaway, more capable of distortion. With the resistor in there, it does, like he says, it damps the circuit down. Yes, we do end up reducing power by a bit because of the resistor being involved in there, but the exchange is well worth the reward, right? How much we're giving up in the power end would be how much more we're gaining in overall stability of the circuit, less distortion, attenuation, and whatnot for our signal. And that would be why you would do something like that. Yeah, no, this chapter's got a lot of we definitely have to keep in mind the overall effect of series resonance. And yeah, we do examine it quite a bit. I mean, how many times are you actually out there in the field looking at Q factors of particular circuits and whatnot? Not so much, but you never know. You could come up with a time where something does seem like it's getting a lot of distortion to it or something like that. And it's good to keep in mind, oh, what's going on here? That in this anyway, and now we get into a little fun actually. So how do you go about choosing which inductor and which capacitor you want for your circuit? So of course, a known value, we need a starting point. So pick one, right? A known value is needed for either the inductor or the capacitor to start calculating out and seeing what our options are. Okay. Like what components. So if we picked a particular capacitor and we wanted a particular frequency, it's like, well, what inductors would work for this and which ones would be more balanced? So we have to take a look at that. So in some cases, right, particularly at very high frequencies, it must be the minimum possible value for the ideal type of circuit. Otherwise, we're losing out in certain ways. Our Q factor will be off or something. And so how do we go about doing this? So at medium frequencies, we do have more leeway. And of course, the lower the frequency goes down, the more room we have to play with. Of course, the higher the frequency, the more likely you're going to have distortion and whatnot. So choosing the proper choosing the proper components, it does become very important, right? So at medium frequencies, we could choose the L for a general case, okay, say, and just say, well, this is close enough, if you will. See, so if we go through this and we find, okay, with this particular one, we have a resonance at 159 kilohertz, right? That'd be our center frequency, if you will. So what we need as far as a cap would be this, and then go through and plug into the formula. Well, with these values, we get our resonance frequency as such. And we could come up with, based on our components, come up with what our Q factor is and examine that. And then we can decide, it's like, well, are these the values we want? So you do have to juggle around with these at times. And there are things, if you were to be doing this as like from a manufacturing standpoint, there are things to take into factor, right? Cost can be a very inhibitive thing, even if you made the most ideal selection of components involved, if your cost factor throws it out, well, I can tell you right now what's going to happen in your circuit. It isn't going to get past the design stage. But that's really what we're looking at. Yeah, and as you can see, this definitely does tie in directly with most communications ends and what we're doing when we tune to particular channels. And it's really, as you can see, it's, well, of course, once we get into radio, yeah, there's a lot more components involved and whatnot. But I mean, at the bottom line of it, really, it's not, as far as making a tuning circuit, it's not very difficult. There's not a whole lot involved. And choosing the components, even if we had a resistor, an inductor, and a capacitor, you're talking a couple of bucks maybe, right? Throw it all together and we got us a little tuning circuit. Now that's not all that's going to go into a radio. This just gets us tuned to the frequency we want. Now, as far as listening, well, that's a whole other ballgame, and there's quite a bit more that goes into that. But at the heart, this is really what you're looking at, where we'd be making basically radio, or I should just say media tuners these days, right? And that's what they do. In any case, so, and that's pretty much the end of the lecture. I will go through and we'll get the homework established for this, right? Chapter 22. And I'm trying to think of the best. See, I don't want to impact. We're not doing any of that take home for the holidays stuff, if you will. I mean, I'm sure you guys are going to complain. I know you want extra work for the holidays, but I'm not going to do it. No. So no, so I would like to basically assign this chapter for the homework. Now, if you like, I could do the chapter and the quiz for this and post it this week and not make it due until, I don't know, like that, maybe that Monday that we come back, so basically you would have like from all this week and all of Turkey week to do the homework and the quiz, which would give you your own you can decide which days you feel like, working on stuff and that kind of thing. So I could do that. I don't, like I said, I don't want to assign work where you got to go up and do some goofy report or something like that over the holidays. It's silly. But yeah, I mean, as long as we don't have any objections, but we can do that where I go through and, yeah, we'll assign the homework and the quiz for this thing, and we'll give you basically it'd be like a week and a half to 2 weeks to do it. And then, and I'm trying to decide. So I may or well, I will have a new lab for tomorrow, and you guys can choose, time frame wise. You're still working on, I know, the series and the parallel and the series parallel stuff, but get through those, and then we'll because we only have a couple of labs left. They're going to be a little more in depth, like as you can see from this kind of thing. And then we have one more. Oh, excuse me, very itchy. Oh, ooh, but we have one more chapter after this one that's important for this. Like I say, the very last chapter, 24. We're not going to do that. That's residential electricity. You got a whole other class to take for that, so we won't even waste our time. We're going to stick with the RLC ends. I feel that's the more important to examine. So, but yeah, that's what we're looking at. And then we only have one more chapter after this. I really don't have any more practice problems per se. I hope everybody. I think we've done really well with what I've been seeing and everything with the practice problems, and I think they do help. You guys have come a long way from when we first started with all this, right? So, so that's how we'll do it, and then and I will see you gentlemen tomorrow morning. And like I say, I'll hand out the new lab, and we'll kind of play it by ear. I'm going to see how everybody gets through it, how we're getting through the labs, and don't freak out. We don't have like very many left. We do have more time to do labs than anything. Um, so, but yeah, that's how we're gonna do that. And then otherwise, you guys have any questions? I will stop sharing this so you don't have to stare at that. You can stare at ugly me instead. Yay! No. But yeah, that's how we'll do that. And then otherwise, I'll just see you gentlemen tomorrow, and then and we'll go with that. Sound like a plan?
Sounds good.
Awesome.
Sounds good, Tom.
All right.
See you tomorrow.
All right. You guys keep warm. Although it does look a little better today, huh? Winter's here, I think. But all right. So yeah, I'll see you guys tomorrow, and otherwise have a good day. And nope, I might have that homework posted today. I might have it posted tomorrow, but it'll definitely be posted between either today or tomorrow. And then the quiz will post it later on in the week, right? And then there we go. But otherwise, I'll see you guys tomorrow. And you have a fantastic day.
Sounds good. You too, Tom.
All right.
Yeah.
Everyone left. Everyone. Well, Will's still there. No, he's not.